physics as the electric field is the minus V. So we choose it the minus because of the regulations, because the protocol which we accepted for the electric energy. We always think that the motion in the physics, I can write all of my statement. In physics, we always think that, we are always wish to think that the motion are going from the lower potential level to the higher one. I mean, from the higher potential to the lower one. So that's the reason the water comes from the head to the ground. Yeah. So we this minus which we use it make a sense about this statement, which the motion are moving from the higher potential to the lower level of the potential. So the first, anyway, I just summarize here that the first operator is the gradient. So gradient phi, or gradient phi, is a simple generalization, the first generalization of elementary calculus. So you have one operator, we call it gradient. Why you call it operator? Because it can act over any functions. So I can forget about what is written here. I just call it this gradient. I can call it this operators. So it's free to act over any functions. You can put it any function here and get the gradient of that. So I want to very quickly present some important identity about these gradient operators, and I will use the information which we already know about the vectors. So let me to review or maybe introduce you some identities about this gradient operator. You know, I need to decide that to main focus more on the physical examples or just spend time to write for you the mathematical expressions. So my interest is that to give the physical example and develop the mathematics during the example. This is my interest. First I find the example and after that I go through the mathematics. But this is what I will do. So for me the example is important actually. And I will go through to find the mathematics which is hidden into these examples. So, but before we needed more information about these operators. For example, I want to teach you something which is not very commonly used today in the texts, but it's some old-fashioned style of working with the gradient, but it still is very useful. I will start by that. Gradient any functions to the some vector. And this vector, I call it vector field. Because this is a function of x, y, z. And it has the same property as the coordinate vector. And has same or similar properties like coordinate vector, x, y, z. Like electric field. Electric field is a vector field. Gradient of any function, but there is no any product here. Any function to the vector is, I want to see that what it will be. Again, I want to back to this new notation of the index. The what which I use it to develop the cross product. You see that gradient phi is partial derivative of x, e1 plus partial derivative of, because this is a vector. So when it's vector, so you can make a representation in terms of the unit vector. This I, j, or e1, e2, e3. This is because this is a vector, because of just this is a vector. I can write it that just to make life easier. just a sigma to make it more compact. And you see that, or even sometimes we write it like that. Just notation, just notation. Each component of the gradient, each component of gradient is just partial derivative of the this with respect to the phi. So gradient phi component of I is just partial derivative of the phi or any function with respect to the xi. What is the xi? Xi is just x, y, z. That's just a simple notation. Because if you don't use the index, we will be like the engineering students. They never use the index. They just use x, y, z to write everything. So if you check the Maxwell book, we published it in 1860 or about 150 years before. So the whole book is written in terms of the component of the vector x, y, z. So the Maxwell equation appear like 5 or 6 pages of the equation. But here we write the equation like the gradient, so it's very compact. I want to use a little bit the modern style. And this is a very modern. So using the gradient is around 100 years before, but using the index is just more recently, maybe 60, 70 years before, in physics actually. So look at that, this is the definition. So to find this, I need to know that, does it have any meaning or no? I have one vector here and I have one vector here. So how I can put two vectors together close to each other without any rule? I mean, for example, A, B, what does it mean? What is the possibility for these equations? So the elementary operation is the normal dot product and the cross product. Huh? The combination of the gradient to the scalar and vector should be defined only in these two ways. You don't have any other options. I mean, here you needed to have a dot, or either dot, or you can have a cross product. There is no other possibility for that. So I needed to do two calculations actually. One is I needed to know that what does it mean that, and what is that. Believe me, these two equations are the important equations about the gradient actually. And not only about the gradient, one of the very important equations in this vector analysis business. Do you know why I first introduced you the cross product into this compact notation? Because I wanted to use it that here. Okay, let me to write this. What is the dot of the two vector? What is the gradient? Gradient of anything is just the partial derivative of that. So partial derivative of this yes. And this is a dot, so it should be dot also, the I component. You know that A dot B is AX BX plus AY BY, so this is the AI BI just. Yes? Okay, this is a partial derivative. Like any other derivative can be expanded here. So one time it will sit with that, after that it will act on this. Like the normal derivative. Normal derivative is derivative of the two functions is first take the first one, multiply the second one, plus the second one, multiply the first one. So it will be sigma I to 1 to 3.